Consider the game you have on your screen, the payoff matrix for A. We're assuming this is a zero-sum game. So we have learned two strategies, domination and minimax. So let's apply to this case. So let's apply first the minimax. The minimax, remember, consider for A, we take the maximum of the minimum on the rows of A. So that means, in our case, is the maximum. For the first row, the minimum is minus 60, the second row is minus 80, and the third row is 40. And the biggest of these three is 40. Player B is the opposite, is the minimum of the maximum of the columns. So on the first column, the maximum on the column is, so this is the minimum of the first column, maximum is 60, second column, maximum is 80, third column 50, and now the minimum of this is 50. As 40 is not equals to 50, we don't have pure strategic equilibrium. What about domination? Let's consider again the matrix and let's write it here. So it's 0 minus 60 minus 40, 60, 0, minus 80, and 40, 80, 50. We check for A. A, we're interested on the bigger rows, while for B, we're interested on the smaller columns. Okay, for A, the first row, 60 is bigger than 0, so this is bigger than this. 0 is bigger than minus 60. But minus 80 is not bigger, so we cannot compare the first and the second. Now, let's try to compare the first and the last. 40 is better than 0, 80 is better than minus 60, and 50 is better than minus 40. So let's write in here 0, minus 60, minus 40, 40, 80, 50. This is 40 is better than 0, 80 is better than minus 60, 50 is better than minus 40. So that means we can remove peacefully the first row because A has no reason to choose the first row, having the possibility to choose the third one. Our matrix gets reduced to 60, 0, minus 80, 40, 80, 50. We cannot choose here 60 is better than 40, but 0 is less than 80. So let's look for B. B wants a smaller columns. So 60, 40. 0 is less than 60. 80 is more, so they are not comparable. Now minus 80 is less than 60. And 50 is more than 40, so they are not comparable. But if we go here, minus 80 is less than 0, and 50 is less than 80. 0 is greater than minus 80. 80 is greater than 50. We want a smaller columns, so we'll get rid of the 0, 80, this one here, and this means our matrix right now has been reduced to, well, 60, minus 80, 40, and 50. And you can check there are no more dominations, so that's the matrix we have to study. From here, in this matrix, A has two possible options, but has no reason to choose the first over the second. On the first, A will do better, A1 will do better, if B plays B1, but will be worse if B plays B2, and similar with B. So what do we do? So what A is going to do, A is going to play strategy A1 a number of times, and strategy A2 another number of times. We'll do this with probability. So we'll write P is a number between 0 and 1, or rather in our case, well, forget this thing. And A2 will play a complementary number of times, which is 1 minus P, which is also between 0 and 1. What A will do, A will toss a coin, say, and we'll play, for example, if P is 0.3, means A1 is played 3 times out of 10, and A2, which will be 1 minus P, 0.7, is played 7 times out of 10. That doesn't mean that the player A will do A1, 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 and then A2 up to 10. No, this is not the correct way to think about it. The way to think about it is that A1 has some kind of a coin that falls 3 times on heads and 7 times on tails, and it will toss the coin, and depending on that, we'll play strategy A1 of A2. So A will play P times the strategy A1, and will play 1 minus P times the strategy A2. Right, so P times this one, and 1 minus P times this one. What is going to do? Find P so that the gains are independent of what B does. How do we know this? The gains cannot depend on what B does. How do we know this? Let's see. If B plays B1, A will win 60 every time he plays the first option, and 40 every time he plays the second option. That's what it will get gains for A. If B plays B2, A will win minus 80 P times and 51 minus P times. So these are the gains of A if B plays B1, and similar B2. Since it has to be independent, what we do is 60P plus 40, 1 minus P equals minus 80P plus 50, 1 minus P. And from here, we get that P is equals to 1 over 15. So this means 1 out of 15 times A1 and 14 out of 15 A2. So the strategies of A are 1 over 15 for A1 and 14 over 15 of A2. How much will it gain? So it doesn't matter, we put 60 times 1 over 15 plus 40 times 1 minus 1 over 15. That's equals to 124 over 3. We could do it here also, but we have put the condition are equal, so there's nothing to worry. What about B? How B should play? Okay, so here is the matrix: 60 minus 80, 40, and 50. So B will play Q times this and 1 minus Q times this one. So in this case, B will lose 60Q plus 1 minus Q times minus 80. Sorry about that. Let me put it properly here. Minus 80 times 1 minus Q. In this case, if A plays A2, this guy will lose 40Q plus 50 times 1 minus Q. What do we want? As before, we want the losses of B to be independent of A. So that means independent of A means 60Q minus 81 minus Q has to be equals to 40Q plus 51 minus Q. And from here, we get that Q is equals 12 over 15. So B should play 12 out of 15 times the strategy B1 and 3 out of 15 times the strategy B2. And that's the mixed equilibrium for this game. We have P is 1 over 15, which means A1 is played 1 out of 15 times, and A2 is played 14 out of 15. Q is equals 12 over 15, which means B1 is played 12 out of 15, and B2 is played 3 out of 15. And we have the value of the game is what we computed before earlier, which is for B was computed here, 124 over 3. So A will gain 124/3 and B will lose 124/3. One warning here, it's just a warning of the way I have been doing the video. A1 and A2, B1 and B2 refer to the 2x2 matrix. It could be different on the 3x3 matrix. It's my mistake, but we'll see it in class or just adjust accordingly.